Hi everyone, welcome to my presentation today. I'll be talking about an empirical analysis of optimization algorithms for MNIST digit recognition. The agenda for today's presentation would be, I'll just give you an introduction about MNIST again, a recap of my previous presentation. I'll be giving the background, the aim, the objectives, the methodology. Then I'll be focusing on the discussion on the results that are obtained in the past 1 month and the conclusion, which consists of a revision of the completed work, the future work, and the challenges I faced. So an introduction, as I told you, MNIST is a bunch of, it's a data set of handwritten digits from 0 to 9. And it's one of the benchmark data sets for evaluating deep learning models. So just a background, we are focusing on deep learning. And most people just focus on the model, right? Can you see the bullet number 4, model? But in fact, deep learning consists of getting a good data set, define a good loss function, and having a good optimization. We can think of it as having the loss function as a goal, the model, the machine learning or deep learning model as a map to get to that goal, and optimization as the search algorithm to reach that goal. Now, what happens is many people just focus on the map rather than focusing on defining what is their goal and how to search for it. Now, imagine you're at a park and you know there's something, you need to search for a treasure. But if you don't define what is the treasure correctly, then how are you going to find it accurately, even if the best map possible? So this study focuses on the optimization part. So we're going to find what parameters of this deep learning model gives us the best accuracy. And that's what an optimization algorithm does. So the aim would be to compare different optimization algorithms empirically for MNIST digit recognition. Now, what is empirical? Empirical means you focus on trials and observations rather than doing theoretical derivations. So the objective would be, I'll be focusing on gradient-based methods. Gradient-based methods means they take the derivatives of the loss function and calculate back propagation based on that. The other type of methods would be non-gradient based, which use simplex methods that you may have learnt in the optimization course taught by Manisha ma'am. So then I'll be focusing on the optimization algorithms provided by PyTorch, which would be ADA Delta, ADA Grad, etc. I'll mainly be focusing in this presentation at ADAM and SGD, as they are the most common optimization algorithms that are used. And I've also excluded LBFGS and sparse ADAM because sparse ADAM only works for sparse inputs, so that doesn't apply for us here. It would change the study topic. And LBFGS is a non-gradient based algorithm which has a very high time complexity, so I didn't focus on that. So the methodology is that I'm focusing on the loss function and accuracy for classification, with the independent variables being the epochs and the training time. The comparison variables would be the optimization algorithm I used, the learning rate I used, and the batch size I used. So just a quick recap of what is a generalization. Generalization is basically the gap between your training error and your test error. So if you look here, in sample error is basically your training error, and out of sample error is your test error. The difference is called as the generalization gap. As you can see, the more and more complicated you make your model, the more generalization gap increases. We want to find the most optimal point where generalization gap is low, as well as where the out of sample error is low. So this is focusing on how to split your data into train, development, validation set, such that you train your data on the training data, you improve the model on your development data, then you compare all the models, all the possible models using your validation data, and only once you use your test data. So just a discussion, I'll be demonstrating the Streamlit app that I had made for exploring all the models. Okay. Ma'am, can you just confirm if you can see the Streamlit app? Okay, great. So as you can see, this is an explorer that I had created for this project. And we have different X metrics and Y metrics. We have a lot of algorithms, but let's just focus on ADAM and SGD. So ADAM and SGD are the most common optimization algorithms. And as you can see, so lower is better. So this is the mean loss for a particular epoch for the development set, basically out of sample error. As you can see, ADAM seems to dominate SGD everywhere. Okay. But this is not very interpretable because loss is not very intuitive for us humans. So let's focus on accuracy. So if you look at accuracy, a similar story can be seen. So as you can see, Adam seems to be better in all cases. Now, an interesting perspective, rather than looking at epochs, we can look at in terms of train time. So as you can see, for larger batch sizes, the training time would be lower because your optimization algorithm is taking more dataset samples in one bulk. So obviously, as you can see, it seems that batch size which is larger tends to be faster in reaching the minimum, minimum loss or the maximum accuracy. So those are some findings. Now, why wouldn't we always use a large batch size? So there are two reasons for that. One reason is because sometimes if your image size is very large, here we are using very simple MNIST digits. However, if your image size is very large, then you can't fit all your images in one single batch into your GPU or your CPU. You will run out of memory. Due to this, you will use smaller and smaller batch size. So the smaller your batch size, the more time it will take to reach to the minimum, the loss minimum, but it will be able to fit into memory. So it's like a trade-off between speed of convergence and the space complexity. So those are just a bunch of studies I had done. And another interesting observation I had made was that there is a algorithm called RProp, not RProp, sorry, RMS prop, which seems to dominate all the algorithms in every case other than batch size of 64 and learning rate as 0.01. The conclusion would be the completed work. Firstly, the learning outcome for this project was that I learned PyTorch from scratch for this project. So I was able to I'm now able to design and deploy a complete deep neural network system from scratch. And of course, the results I had shown, which showed that Adam seems to dominate SGD in all cases. Of course, maybe there could be a different combination, maybe for a different problem, the SGD could be better, but in this particular study, Adam seems to be better. The future scope would be that we could use different dataset sizes rather than focusing on the entire set. Maybe if we train the model on 10,000 samples, maybe the results may vary. We could try different architectures because here I just used a very simple fully connected neural network. The main challenges for this was that the competition cost is very high to try out all these possibilities. And of course, energy cost and time. Those are the main challenges. So thank you, and like to ask if you have any more questions, you can ask. Sure, ma'am. I'll just show you. So you're asking how am I visualizing this? Is it? So this is a library called Plotly, and the app platform is called Streamlit. So Plotly is a interactive visualization tool written in JavaScript. So it allows for very complicated visualizations in very small syntax. So as you can see, I was able to make a grid of different learning rates with respect to different batch size. And the cool part is that if you move one axis, it updates everywhere. So let's say I would like to only focus on ASGD and let's say N Adam. I can zoom and pan in whatever way I want, such that we can only focus on these two.